First, let's talk about the NAND gate. And a NAND is literally just the opposite of an AND. So that means that we can write the logic expression as XY here, but then invert that output, or the opposite of an AND. And through De Morgan's, we know that we can write that another way as X naught plus Y naught. Break the line, change the sign. Additionally, if we take a look at when the inputs are both true or when the inputs are both false, we see that when those inputs are the same, the output is going to be opposite of whatever the input is. So when both inputs are 0, we get a 1. When both inputs are a 1, we get a 0 as our output. And what we have created here is a NAND gate that is an inverter. So if you take a look at our legs of our inputs there, they're tied together so they can only be the same, and our output is just going to be the opposite of whatever our input is. So here we have a NAND gate, and we know that the output of the NAND gate is going to be XY, the quantity knotted. And then if we run it through an inverter, here's a NAND inverter, we're going to have the quantity XY not, and then we're going to have another not to that. And we know when we have double inversion that we can eliminate that, and we end up with just XY, which is an AND. So effectively here, we have used a NAND gate and then a NAND inverter to create an AND gate. So here we have two inverters. So we have an X naught, we have a Y naught, and those are feeding into a NAND gate. And so our output here is going to be X naught, Y naught, the quantity knotted. And if we start to apply De Morgan's here, we're going to break the line, change the sign, and we end up with X naught naught plus Y naught naught, which we know we can get rid of those double inversions, and we have X plus Y, which we know is just the logic expression for an OR gate, and you can see that our truth table matches that of an OR gate. So what we've done here is we've used an NAND gate to create an alternative version of each an AND, an OR, an inverter. So if we use a NAND in a very specific manner, we can replace an AND, replace an OR, or replace an inverter with just a NAND or series of NAND gates. So here we've got this circuit that is BC naught plus AC, and we'd like to convert that to NAND-only logic. In order for us to create our NAND-only circuit, we're going to take our AOI logic gates and replace them with their NAND equivalent. So for this inverter, we're going to replace it with a NAND inverter. For these two ANDs, we are going to replace them with this block that is a NAND and then a NAND inverter. And then for the OR gate here at the end, we're going to replace them with this block, which is two NAND inverters feeding into a NAND, which we know is the equivalent of an OR. So here's our resulting circuit, and you're going to take a look at this and go like, why would I want to do this? I have extra logic gates. It took me more time. What's the benefit? Well, if you take a look here in the center, what we really have is some double inversions occurring. We have a NAND inverter feeding into a NAND, directly into a NAND inverter. And anytime we have a double inversion, we know that we can cancel that out. That's actually equal to what it is at the previous. So we can cancel out both of these double inversions, and we end up with actually a simpler circuit. So here I have my simplified NAND circuit, and let's trace the logic. So I have BC naught, the quantity knotted. I have AC naught quantity, and then I have BC naught knotted times AC naught, the quantity, all inverted. If I perform some De Morgan's to that, break the line, change the sign, I end up with something that looks a little bit like this, has a couple of double inversions to it. If I get rid of those double inversions, I end up with BC naught plus AC, which, as you'll remember, is the same as the previous circuit. So again, you'll ask, but why would I go through all this effort if I'm just getting the same circuit? But if you notice, I have only one type of logic gate here, and that's going to be of big benefit to me. If I compare my two circuits side by side, we see that the first one requires two ANDs, one OR, one inverter, which requires me to have one of each type of chip, or 3 chips in total. For my NAND circuit, I have 4 logic gates, but that's only going to require me 1 chip, which is going to save me some big money overall, and certainly some time when it comes down to breadboarding it. So you'll see that this is oftentimes the legwork up front is going to save you in the long run.